Hello and welcome to our presentation. We are presenting The Forgotten in honor of the forgotten astronaut, Apollo 11 legend, Michael Pollan. We are Team 4 and our name is full nickname. And starting from the top left, excluding Devin because he couldn't make it today, we'll start by introducing our names.
Hello, I'm David.
Hello, I'm Bennett Richmond.
Hi, I'm Drew Rosales.
My name is Olga Khmelnitsky.
I'm Chris Shells.
I'm Andrew Liu.
Hi, I'm Duran Khan.
I'm Michelle.
And this is a really brief overview of our team organization chart, and we'll touch more on it later.
So part of this mission, we got a couple of constraints from NASA, but additionally, we developed a couple of other guidelines that we'd like to focus on as a team. So the first of which we received from NASA, and that being for at least one PSR, we'd like to get at least plus or minus 1 accuracy. Additionally, we'd like to map out about 95% of all of the PSRs on the south pole of the moon. Additionally, our team added 2 things. First, we would like to look into the mineral salt composition of water ice, and then also be able to get some sense of the form of water ice underneath the lunar surface. From NASA, we also received a couple of constraints. Our team decided to go with the Rover path. And for the Rover, we got constraints for mass, volume, and overall budget for the mission. And also that our rover would start from about 10 kilometers off the lunar surface, and the mission would run collecting data and the rover traversing the lunar surface for about 2 to 3 years. Next slide, please.
So for this mission, we chose a stretch of PSRs encompassing 2 known craters, Sverdrup and Gerlach, as well as 1 unnamed PSR valley and 1 unnamed PSR crater, as you can see by this green line, indicating the route of the rover. This route was chosen since it is the longest stretch of PSR without major incline or rough passage. In fact, the largest incline angle to be faced is 27 degrees. Forgotten will be landing in the unnamed PSR valley since it is the flattest part of the route, where it will complete all calibrations and testing of the equipment. Once the rover completes measurements in these PSRs, it will assess which direction is easiest for it to proceed in, taking into account how much power it has left. Next slide.
So for our descent vehicle, we opted for a sky crane-like design with 4 MR-107S engines. They are hydrazine monopropellant engines, and in total, they produce 216 meters per second of delta V for us to land on the surface. For the rover body, we needed a strong yet light material, so we went with a carbon fiber composite.
The computer contains a RAD 6000 CPU and various forms of memory. It will directly interface with all of Forgotten's instruments for an exchange of commands and science data. It will register temperature and power levels to make sure Forgotten remains alive and healthy. It will use flight software to perform all operations necessary to facilitate the science objectives. The cameras on Forgotten are 2 hazard avoidance cameras, 2 navigation cameras, and 1 catch cam. Similar to Perseverance rover, the hazard avoidance camera will aid in autonomous navigation by identifying potential obstacles and steering Forgotten onto a safe path. The navigation cameras will also help in autonomous navigation, but it will also be used as the main visual for navigating in real time by the ground team. The catch cam will take images of the electrodes from the vertical electrical sensing system as they are placed into the lunar surface to confirm or deny their placements. The LEDs are Cree white light LEDs that have 2 purposes: a set of 6 LEDs in the front of the rover that act as the headlights of our vehicle, and a set of 3 under the rover that light up the electrode placement area. Next slide. The UHF antenna, a form of low gain antenna, will be our main source of communication. It will communicate directly with the orbiter as they both have frequencies that are in close range with each other. The low gain antenna is a secondary communication source to the UHF antenna in case of a failure. The low gain antenna transmits radio waves at a low rate to the deep space network antennas on Earth. A huge benefit of using low gain antennas is that they can send and receive information in every direction. The high gain antenna is another way we can communicate with the ground team. It uses its ability to steer to communicate with Earth to receive commands for the mission in real time. Next slide. The custom wheels we have on Forgotten are based upon the upcoming Viper rover mission, which are designed to add traction and minimize lunar dust collection within the rim of the wheel. Our design is made out of titanium because it is stronger than aluminum and the weight constraint allowed for the upgrade. The motor, gearhead, and sensor are from Maxon, a company that has provided motors for other rotorcraft projects. The motor is a brushless motor that has very high torque density, which we want, and excellent dynamics. Next slide.
So powering our rover is an MMRTG, which we adapted mostly from Mars Perseverance. But the main reason is due to the fact that we're in a permanently shadowed region, so there's no sun, so we can't use solar. And it also provides a constant source of heat for the interior of the rover, so to protect the computer and other elements from the lunar environment. And then we spoke with the NASA RPS facility, and they also confirmed that while they're not working on it specifically, the GPHS modules can be lessened from 8 in Perseverance down to 2, which is more, which fits our mass and our mass constraints more. And then on top of that, we have a lithium-ion battery, which will provide backup energy to the rover. Next slide.
Forgotten contains 5 different thermal control systems to maintain a regular temperature inside Forgotten, from the freezing lunar temperatures and extremely hot radiation from the RTG. The heat piping system is a 2-pipe circuit-like loop that is connected to the RTG. The inner pipe is directly connected to the RTG cooling tubes to provide a constant flow of trichlorofluoromethane, and the outer pipe is connected to the RTG to allow an escape route for the high levels of radiation it produces. The ambient atmosphere allows conduction to occur inside Forgotten. To do this, we put gas molecules into the closed system rover body. Some options for gas particles that are great for heat transfer are air, argon, boron trifluoride, and oxygen. The insulation around the inner layer of Forgotten's body is silica aerogel. Silica aerogel is a very effective thermal insulator that will be used to keep the heat inside the body of the rover. Because of the freezing temperatures in the lunar South Pole, Forgotten must maintain a set temperature between 0 degrees Celsius and 10 degrees Celsius to keep all the instruments alive and healthy. The thermostat system in Forgotten is a multi-purpose logistics module programmable thermostat. This allows greater flexibility and thermal control in the rover. The heatsink system contains a large heatsink and a radiator. The heatsink is made out of a 5x5x5 inch aluminum 6061-T4 block with a carved tube-like design. It is designed specifically to allow the heat piping system to release some heat through conduction before connecting back to the RTG, completing the circuit. The radiator is directly connected to the heatsink by a thermal paste, and its purpose is to expand the surface area of the heatsink to allow more conduction transfer to occur. Next slide.
So with all these systems here, there are a lot of chances for failures. So we chose a select list here of different phases in the mission where things could go wrong. The first is with the descent engines, and if one of those fails, we have calculated that the rover can land with 3. And then once on the surface, if one of the wheel motors fails, each of the other wheels has a separate motor, and it still can navigate with just those 3. And then with the science systems, if our electro deployment system fails, the vests unfortunately won't work, but we do have our looser ground penetrating radar system, which can provide at least some backup science data. And then with the RTG, if that happens to overheat the interior components, as Bennett mentioned, there's a lot of thermostats and a pretty robust cooling system. So it should be able to maintain the proper temperature. And then finally, as Bennett mentioned, if one of the antennas is damaged, either on the landing or in transit, we do have 2 others. So there should be plenty of backup systems. Next slide.
So this begins the payload and science instrumentation section of the presentation. Next slide. So firstly, I would like to start with a brief overview of the science instrumentation lineup and the action plan of the mission. This section will be followed by the detailed reviews of each science instrument by their creators. Once the rover descends, and the descent vehicle is launched off the rover will begin calibration and startup of its first science instrument, which is the Lunar Subsurface Radar, or LUSR, followed by calibration of the vertical electrical sounding system, VES, and the deployment of the first electrodes across the lunar surface. During this, the water ice spectrometry equipment will be in lunar orbit while conducting its measurements. The rover will then reverse to retrieve the electrodes and redeploy them at different distances or different configurations. The LUSR will always be on during the rover, whether it is stationary or moving, and it will be collecting data during this process. Next slide, please. So I'll begin by talking about VES. VES is a system that is based on the guiding principle that different substrates have different resistances when a current is passed through them. This allows us not only to measure the abundance and the distribution and the specific location of the water ice, but also the mineral salt concentrations of that water ice, as well as what state the water ice is present in, whether it's slab-like or saturated within the rock. The methods we chose to perform is the Schlumberger array method, since it provides the best data with the best deployment and the easiest deployment. The two outer electrodes, A and B, will be the current inducing electrodes, while the two inner electrodes, M and N, will not have current passing through them, but rather will measure the changes in potential as the current travels through the lunar subsurface. The subsystems of VES can be narrowed down to data storage, electrode deployment and retrieval, and the resistivity meter. The data storage contained in VES can allow for storage of up to 79,000 resistivity measurements. It also includes a microprocessor that contains calibration values that can be assessed at any time and accessed during any point of the mission for recalibration. The resistivity meter will be connected permanently to the cables and will read the measurements and process them for noise suppression. Then it will send data to the orbiter and back to Earth. Next slide.
The deployment system for VES consists of electric linear slide actuators, an electrode arm design, and a containment box. The electric linear slide actuators are from Oriental Motor, a company that provides various types of motors and actuators. The electric linear slide actuator we chose contains an electromagnetic brake to help with stopping the actuator. The electrode arm design is an aluminum 6061-T4 pipe design connected to the electric linear slide actuator, and at the end of the pipe, a claw-like design to force the electrode into the lunar surface and also is able to pick them back up once completing the task. The containment box is to separate the rover into two sections, a closed system and an open system. The closed system contains all hardware for Forgotten, and the open system contains the electrodes and the holes. Next slide.
So to analyze the data, we'll be using AGI's Earth Imager software. Depending on the number of successful completions of the measurements that VES will be able to produce, as well as the number of planes that the electrodes will be deployed in, we can either get 2D data or 3D data. But regardless of what type of data we get, we can still make observations of the mineral salt concentrations, as well as the state of the water ice in the subsurface, as well as manipulate this data to take into account the topography of the lunar surface where the measurements were taken. Next slide, please.
I will be talking about the Lunar Subsurface Radar, LUSR. It is based off rim facts from the Mars Perseverance mission. LUSR will be able to send its radar waves into the lunar surface through antenna transmission to gather data to create a 2D scan of the underground. The control unit is the computer behind the process. It is responsible for sending out the pulses and setting the wave strength. After the waves have been detected, have detected the water ice below, the waves will be reflected back towards the receiving antenna, and then the gathered data will then be collected and stored together to be filtered and ultimately sent back to Earth for analysis and further processing. Next slide.
The final instrument that we have is the water ice spectrometry equipment, or WISE, and this is based off of the LAMP instrument, which was featured on the Lunar Reconnaissance Orbiter. And the idea of this instrument is it takes in far UAV from starlight, reflects it onto the surface of the moon, and then that UAV light excites molecules within the water, specifically hydrogen. And once it comes down from the excited state to the ground state, it emits a photon, and that's how the water ice can be detected. This instrument is split up into 3 different parts, including water power management, data collection, and the optical mechanical part. On the bottom right-hand portion of your screen is a listing of the optomechanical portion. Light enters in on the right-hand side of the figure, and then it enters this aperture door, which can be tweaked based on the conditions that the instrument is collecting light. It is then passed on into a mirror and grading system where magnification takes place, and then the light is split up into various different wavelengths with the diffusion gradient, then enters in the detector, which includes a spectrometer. This instrument will be featured on the orbiter. We thought that we could take further advantage of an orbiter, which is in place for the rover to communicate with, which has a 100-kilometer circular orbit. And we wanted to do this so that we have a better mapping of the lunar surface. And overall, the data is collected in XY position. And there's also a timestamp, which triggers when the instrument thinks water ice is found. Upon that getting triggered, there's a histogram mode, which actually shows the different wavelengths and its abundances, which helps to keep track of information on the lunar surface. Next slide, please.
So as a safety officer of Team 4, we have decided to utilize a 3-part plan in ensuring the safetyness of all personnel and members working on this rover. This 3-part plan encapsulates risk assessment, capability assessment, and mitigation strategy for all equipment and use in the development of our rover. This information could be found in an Excel sheet where there are 3 fields, 3 columns. The first column being the equipment name, second column being the risk and potential hazards of that equipment, and the third column finally being the solutions and hazard mitigation to those dangers. It is also worth to mention that Team 4 is completely compliant with the Federal Occupational Safety and Health Administration.
So there lay quite a number of risks present during the expedition phase, 4 of which I've decided to focus on. Firstly, we have the lunar dust, composed of mostly silicon dioxide glass and negatively charged as a result of the solar radiation. Lunar dust becomes highly abrasive and adheres to nearly any material. To combat this, a thin layer of indium tin oxide will be applied to the outer layer of the rover to dissipate any unwanted electrical charges. One of the next problems is the temperature swings, which vary over 300 degrees Celsius in 1-day cycle. We designed the rover to have sufficient insulation, an efficient heat piping system, as well as the design of a closed system in order to prevent the instruments from freezing or overheating. When undergoing temperature testing, the rover will go through 11 cycles with plus or minus 10 degrees on each extreme. Next, although the exact number is unknown, studies have shown that substantial numbers of rocks and other debris striking the lunar surface every year. To prevent internal damage, the science instruments will be placed in areas of low risk within the rover body. Lastly, one of the largest concerns is mobility. Due to the lunar surface of the poles remaining relatively unexplored, scientists are still uncertain if the lunar regolith would be soft, hard, or a mixture of the two. In order to best prepare for unknown circumstances, the rover will have, as aforementioned, separate motors and are able to act independently of one another. Next slide, please. The general mission life length is roughly just over 5 years. Although a good estimate, these dates are very tentative as the researching and manufacturing timeframes are subject to change. The phase lengths were based mainly on other projects to give the most accurate results. The rover's RTG component gives the rover the lifespan of around 2.5 years. Next slide, please. Overall, the total project came out to be just above $112 million, which is roughly 56% of the allotted budget. All prices regarding manufacturing and materials were matched as closely as possible to similar technology of similar specs. Anything that could not be found reliably was calculated using the NICM model. For personnel, due to everyone not needing to be working for the entirety of the project, costs were able to be cut. Margins were also added using a 50% additional cost for manufacturing with 28% for staff and an extra 30% for the total cost. Next slide, please.
So as previously mentioned, Team 4 was divided into a hierarchy structure as shown in the organizational chart, with at the top being the project manager, then to the deputy project manager, then to the following leads, lead scientists, lead admin, and lead business administration, and then following that, all the researchers, engineers, and scientists working on this project. Team 4 places a heavy emphasis on team collaboration, but not all teams are perfect, and as a result, we do have some team difficulties. With that being different backgrounds and specializations, the threat of COVID-19 and communicating online, as well as time complexity and meeting deadlines due to personal obligations or just random events. As for future works, Team 4 is looking to satisfy all the conditions in the conditions development document as the next step, as well as working on the rover to either improve, add, or optimize several of our equipment. This includes electrode testing for lunar surface penetration, heat rejection systems, reducing the size of the MMRTG, or adding additional equipment.